In our previous video, we ended with this outline for how to find absolute maximum and absolute minimum values of a function on the closed bounded interval. We identify the critical points when the derivative is equal to 0 is undefined. We evaluate the function at those critical points. We evaluate the function at the endpoints, and then we choose which ones give us the largest and the smallest values. Let's do a couple examples of that. So for our first example, let's suppose that our goal is to find the extrema, the absolute max and absolute min of our function is f of x is 2x cubed minus 15x squared plus 24x plus 7. And we have to say what the interval we're going to try to optimize this on. It's the closed interval 0 to 6. Continuous function on the closed bounded interval. We know from our previous theorems that we are guaranteed to have absolute max and mins from this theorem here. And we also know that the only places we have to check from this theorem are critical points and endpoints. So once again, from this slide, we have to identify the critical points. So f prime of x is 6x squared minus 30x plus 24. This is never going to be undefined, so our only critical points are going to be when this is equal to 0. So let's solve this. The coefficients here all are multiples of x. Sorry, all are multiples of 6. This factors as x minus 4 times x minus 1. And so we see that we have two critical points. And that's x is equal to 4 and x is equal to 1 are our critical points. So our next step is we want to evaluate our function at these critical points. So we're going to say f of 4. When we plug 4 into this expression up here, crunch, 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 you end up with minus 9. When we plug in 1 into this expression up here, check for yourself that you get 18. But we can't just limit ourselves to the critical points. We also have to evaluate the function at the endpoints here. So our endpoints are 0 and 6. So f of 0, plug 0 in here, we get 7. And our other endpoint is 6. And plug 6 in here, we end up with 43. So we evaluate our function at critical points, we evaluate our function at endpoints. The last thing for us to do is to choose. So we're going to choose which ones give us the largest and the smallest values. And from the list of these four numbers, minus 9 is the smallest, and 43 is the largest. So what does that tell us? This gives us the absolute min and the absolute max. So what we're doing here, this is great because this outline here, we want to try to optimize our function at closed bound interval. The only place we have to look are critical points and endpoints. So we've reduced our problem down to just looking at 4 points here. If you want to see a graph of what this looks like, it looks something like this. Between 0 and 6, we see our absolute minimum at 4. We see a local maximum at 1 here. But so we check here, 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 and here, and we find our absolute min and our absolute max. So that's one example. Let's do an example where our critical points, some of them might be undefined. So let's suppose that we want to find extrema of f of x is equal to 1 minus x minus 1 to the 2/3 on the interval -1 to 2. So as before, our first job is to identify the critical points. So to do that, we have to take the derivative. F prime of x is equal to -2/3 times x minus 1 to the 2/3 minus 1 is to the -1/3 power. We could rearrange this as -2 over 3 times x minus 1 to the 1/3. So we can ask, when is this equal to 0, when we're trying to find critical points? Well, a fraction is equal to 0 exactly when the numerator is equal to 0, and the numerator is -2. There are no points at which this function has derivative equal to 0. However, we also have to think about if the function, if the derivative is undefined here, and this is going to be undefined exactly. F prime of x is undefined when the denominator is 0, which is when x minus 1 is 0, which is when x is equal to 1. So, x is equal to 1 is a critical point. In fact, it is the only critical point of our function. So we have identified the critical points. Also, something I didn't do in the last video, but I should have, but I'll do right now. We always want to make sure, is our critical point inside the domain of our function? And so the answer is yes. X equals 1 is between -1 and 2. If our domain was something like from 5 to 7, then 1 would be a critical point, but not in the domain, and we could safely ignore it. Okay, so where are we? We identify the critical points. There's only one. So now we have to identify the function at critical points and at the endpoints. So what do we end up with? F of 1 is, plug in 1 up here, we get 1. And we plug in -1 in here, so that's our first endpoint. Plug in -1, it's about -0.59. And we plug in 2 in up here, we end up with 0. So we have evaluated function at a critical point and at the 2 endpoints. So the last thing for us to do is to choose. So 3 possibilities. This one looks the biggest and this one looks the smallest. So absolute maximum and the absolute minimum. If you want to see a picture of what this looks like, so you can see here clearly the cusp that is occurring where the function's derivative is undefined. Okay, to finish off this video, I had to track down my pre-class problem. Slipped onto the floor, so here's our second pre-class problem. I want you to find the absolute maximum and absolute minimum values of x cubed minus 3x plus 2 on the interval from 0 to 2.